Fundamental theorem of algebra. The fundamental theorem of algebra states that if fx is a polynomial of degree n greater than 0, then fx has at least one complex 0. We can use this theorem to argue that if fx is a polynomial of degree n greater than 0 and a is a non-zero real number, then fx has exactly n linear factors. So that's what we're getting at in the last video, how it touched on that with the linear factorization theorem. And now here it's being formalized, and it's saying that if fx is a polynomial of a degree n greater than 0, then fx has at least one complex 0. Now, an interesting thing here, let's say I had the polynomial fx equals x plus 2. The 0 for this is equal to negative 2. Now, the reason why they can get away with saying a complex 0 has at least one complex 0 is this is a real number. And actually, the real numbers are contained in the complex numbers. Because if you notice, a plus bi, I have a real part and an imaginary part. So in that sense there, if my b is 0, I can still look at a real number a as a complex number because it's actually contained in the complex numbers. Just like if I had an integer is just a negative or positive counting number. And I know that's actually contained in the reals. And z represents integers, just so you know. And that's a part of the reals. Another part of the reals is the rational numbers. Those are all the fractions. That's an integer over an integer. Okay, but if I was to get specific on that, I would have to set this a certain way because there's a nesting that goes on here with q and z even. But I just kind of wanted you to get the gist of what we're dealing with here. So to say at least one complex 0, I have to understand that the real numbers are contained inside of the complex numbers. So just be aware of that. So that's what makes that okay to say. Now, what's nice about this is now I know every polynomial can be broken down to linear factors. So let's take a look at this problem. It says given f of x equals x to the fourth plus 5x squared plus 4. Part A says find the complex zeros. So I know I'm going to have 4 because this polynomial is of degree 4. So what we have to do is we have to try to find those now. Now, one thing I noticed right away is that I have a degree 4 here, a degree 2 here, which is half the power of the first term, and then I have a number on the end. Since I have this pattern, I can use the quadratic formula here. In the quadratic formula, if I can find the zeros, I can find the factors. And that's my first step I can do here. Another approach I can take is I could use the rational zeros theorem and see if there's any rational zeros here. And then I can go from there. Not sure which one I want to try first because I'm not sure all of these roots are going to be, even if any of them are even going to be real. I might get 4 complex roots. So I'm not sure where I want to venture with this one. So if I think about negatives or positives, and again, if I did the P over Q idea here, which I'm just going to kind of give you an idea of what that looks like. On the bottom, I get plus or minus 1. And on the top, I would get plus or minus 1, plus or minus 2. And then plus or minus 4. And then if I go through those, I'll realize that when I plug them in, since these are even degree polynomials there individually, that it's always going to result in a positive number, so I'll never get a 0 this way. So that tells me there that I'm not going to deal with a rational 0 here. So that tells me the quadratic formula is definitely way to go here. And I can use it because I have this power of 4, and I have this power of 2 next, which is half the power of the 4, and then I have a number on the end. That pattern tells me I can use the quadratic formula. So that means my A equals 1, B equals 5, and C equals 4. And essentially, I'm just going to plug that in here. X equals negative b, so negative 5 plus or minus the square root of b squared. So I'm just going to put 25 minus 4 times a times c. And that's all over 2 times 1. Now this is going to be negative 5 plus or minus. So that's going to be the square root of 9, because I'm going to get 25 here minus 16, which actually this works out beautifully. Now the thing is with the rational zeros theorem is I'm talking about linear factors. So I'm talking about a zero that's of degree 1 in a sense, if I think of that, or multiplicity 1. And this is going to be negative 5 plus or minus 3 over 2. So now these two numbers I get for my x, now these are going to be zeros for x squared, but not for x. And we'll see what that means in a minute here. So let's finish this up. So this is going to be negative 2 if I add the 3 over 2, which equals negative 1. And the other answer is going to be x equals negative 8 over 2, which is negative 4. So how this works here is my f of x can then be factored into x squared minus 1, or plus 1, I should say, because negative 1 is a 0 for that x squared. And then the other factor is going to be x squared plus 4, because honestly, this is really a x squared, x squared, x squared. And that's what we're really dealing with here. So the x squared is actually 4. I'm not plugging it in for x, and that's why I said that. And that's how we play the role with half the powers. So it's not a direct, my x is this. So I wanted to kind of point that out. But I started out with x equals using the quadratic formula. Another way I could have done this is I could have just looked at this and said, hey, let me break it down. I know this would have to be an x squared, and that would have to be an x squared. And then I look at 4. What are my factors of 4? And then they have to add up to be 5. And I might reason that I get a 1 and a 4 here. That's another approach. But again, I can always use the quadratic formula if factoring is a hard thing for me. And the idea of the zeros works when you're talking about moving it over to the factors, the zeros for the quadratic formula. So that's how it works. So this is what it factors into. Now I have to go further than this. Can I factor this more? And I can just look at where the 0 x squared plus 1 equals 0 here, if I'm going to find the zeros. And then what would I do? Move the 1 over, so I get x squared equals negative 1. I would square root both sides, and this is the easiest way to do it. So then I'm going to get x equals plus or minus, should have put equals first, plus or minus square root of negative 1. And square root of negative 1 is I. So this means plus or minus I. That's what I end up with for the first one here. Now for the next one, I do the same thing. I'm looking where that's my 0. So x squared plus 4 equals 0, because I want to find out where this is 0 now. Okay, so then I move the 4 over. I get x squared equals negative 4. And then I square root both sides. Then x equals plus or, I did it again. X equals plus or minus I square root 4. And then that's going to be x equals plus or minus 2i. And that's what we're looking at for the other ones. So now if I put all these together, because keep in mind, what am I looking for here? Finding the complex zeros. So that's what I want to do now. So I'm going to take those and say, okay, my complex zeros, or just say zeros, are, and I need 4 altogether here. So I have 2 here, and I have the other 2 here. So now I can just formally write them. So negative I should just write I. I don't have to put positive I. Negative 2i and 2i. So those are my 4 zeros. So there you go. So that's my part A. So I just had to find them. I could use a quadratic formula. I could just factor. I could take this in different ways. So just kind of be careful with that and make sure you're justified if you're going to use the quadratic formula. And I do like the quadratic formula, but just be aware of what you're actually finding when I find that -1 and that -4 there for the zeros. And that's why when I tried the rational zeros theorem, see, that would have resulted in just 1x minus c. But see, we didn't get any real c's. They were all 4 were complex zeros. That's why that didn't work for us. But it's always worth a shot to take a crack at those. I usually do because it makes it easier if they are. But I don't have to use them. I just want you to be aware of that's still there. That's a tool we have now. Okay, so anyways, let's get into part B now. It says write f in factored form. So now this is easy. Once I have that, all the zeros, the factors are nice. So that's going to be equal to, and I'll say x plus I, and that's for this 0 here. Because remember, it's always the opposite sign. I hate when people say that, but it's usually how they think of it. I think of it this way. What makes it 0? Negative I, and that's my 0 there. So that's how it works for me. That's a better way to think about it. So this is going to be minus I. I guess I don't know if it's better, but for me it seems better. So that means if I plug that positive I in here, it's going to make it 0. Okay, the next one's going to be x plus 2i. And I'm just going in order of the zeros I have there if you're interested. Now, you don't have to, but I want you to be aware of what this 0 is producing, because if I just have these two, I want you to know how that works. So that would be my factored form of f. Once I have the zeros, the factored form is really just writing it out and understanding what the zeros are and the factors from those zeros are. So that's our answer for part B.